So, in the last class we defined Boolean circuits, and we showed we first defined these problems which can be solved by size Tn Boolean circuits for growing n input size, and these problems we collect and form a complexity class called size of t, size bracket Tn, right. And we also showed that this non-uniform hierarchy theorem or hierarchy theorem for circuit sizes does exist. It is almost as good as the deterministic time hierarchy theorem, but has a different proof. The proof here is by counting. Okay, we did not use diagonalization method, but counting method. It's not very clear whether diagonalization trick exists here. And then by collecting polysize circuit families, we get this P/poly complexity class, which is the analog of polynomial time, but now it is for circuits, Boolean circuits instead of Turing machines. And we were proving that P is contained in P/poly. So, this is just a proof sketch. I will not go into the detailed proofs. It is actually not difficult to finish these proofs. So, P is contained in P/poly is done by the following. So, let x be input, x be the input of some fixed length n, and whatever the Turing machine does, so each step of the Turing machine m on x is very simple, right. It is just one bit changed in head moving. So, that can be easily implemented by AND or NOT gates. So, each step of the Turing machine mx can be written as can be implemented by gates. AND or NOT gates. And then you go over all the steps. Remember, n is fixed for this, right. So, this will give you a circuit Cn. We find a circuit C, we convert mx into circuit Cnx, and it is easy to see that since the number of steps is polynomial in n, the circuit family Cn as n grows is poly n sized. Okay, so that means P is contained in P/poly. And so all efficient algorithms, they actually live in P/poly. Is that all? So, surprisingly, because the way P/poly is defined in a non-uniform way, you can actually have a completely different circuit for length n and length n plus 1. So, in particular, so first of all, observe that there exists a unary language L that is uncomputable. For example, L which has those unary strings 1 to the n such that n describes a Turing machine that halts. So, if you take this language, then clearly this halting problem reduces to this. So, L is uncomputable. And now what you do is you have a trivial circuit Cn which will accept only on when 1 to the n is in the language, otherwise it will reject. So, the circuit family Cn such that Cnx is 1, Cn is 1 if and only if 1 to the n is in L, right. This is this solves L. Right. So, and it is of constant size, in fact, not even P/poly. So, this has constant size circuits solving an uncomputable problem. Right. So, that shows you the power of non-uniformity. This is the power of non-uniformity. Because we do not know how to produce Cn, but Cn exists, right. So, this is the, it is a non-uniform circuit family. It cannot really be produced, but it exists, and hence P/poly can solve uncomputable problems. It can solve the halting problem. So, it allows us to hardwire the answers. So, without knowing the answers, they can be hardwired, right. Without computing the answers, you are just hardwiring it, and so they exist, circuit exists. Okay. So, P/poly is an important class. So, we will define it in one more way. So, P/poly is an important class let us define it via Turing machines. So, instead of using Boolean circuit, we can also use Turing machine, and then it will be called Turing machine with advice. So, let us define that. What is advice to a Turing machine? It is something like Oracle Turing machine, but weaker. Okay, so this will actually be somewhere between non-deterministic Turing machine taking advice and Oracle Turing machine taking advice. So, it is also called, we can also call it non-uniform Turing machine. So, a decision problem L is in D time Tn by An if there exists a Turing machine M such that for all input x there exists so T and A are functions, right? T is the time function, A is the advice function. So there should exist an advice which is a string alpha n of that much length such that m given x and the advice is 1 if and only if it's a yes string. Okay, so basically what is happening is alpha n is some kind of a certificate, and when it is provided, then m will be able to identify x as yes or no string. The key thing here is the difference from NP is that this alpha n doesn't depend on x. Okay, it only depends on its length. It is not a function of x, it's only a function of n. And the time, obviously the time of m on x is t of x. Okay, so m is a Turing machine that takes t n time on n sized input x, and it works correctly if it is given advice for that length. Okay, not for x but for that length. So that's the important point. So alpha n doesn't depend on x. It only depends on n. So only on the length n equal to x. The same advice for all the inputs. So that is a difference from NP. So this you check as an exercise. How is this different from NDTM definition or Oracle definition? Okay, you can see the differences. So that defines d time Tn, and then using this we can define p/poly by limiting t and a to be polynomials. So we can actually put this as a proposition. That p/poly defined via Boolean circuits, poly-size Boolean circuits, this is actually equal to union of d time n to the c slash n to the d for all constants CD. Okay, so this is another way to define p/poly using Turing machines. So here there are no circuits, right? This is just by Turing machines. So let's do the forward direction. Say L is in p/poly. So why is L in this d time, this Turing machine with advice? Well, so since L is in p/poly, it means that L has poly-size circuits Cn, and you just give this Cn as advice to a Turing machine. So we can give Cn as advice to a universal Turing machine, to a Turing machine that on x of length n simply computes Cnx. And hence solves for whether x is a yes string or no string. Okay, so this means that, I mean, since Cn was of poly size, this means that to a Turing machine M. So this means that time of M is so there exists CD such that time of M is less than equal to n to the C, and the circuit size is n to the D. And so it immediately tells you that L is in D time n to the C slash n to the D. Okay, so hence it is L, if L is in P slash poly, it is also in the right hand side. And let us do the converse. So say L is in D time n to the C slash n to the D. How do we show that L is in P slash poly? So from Turing machine, we need to go to circuits now. So Turing machine M x comma alpha n solves x in L problem. Okay, so there is this polytime Turing machine n to the C time, or order n to the C time Turing machine, which will solve big O of n to the C time Turing machine, which will solve whether x is a yes string or no string for advice alpha n. Which is of length n to the D. That is what is given to you. So let us define circuit Cn as the circuit that computes basically it computes the, or it simulates M on any input given alpha n. On every input on arbitrary x 0 1 to the n. Okay, so given any input of that length, there is a fixed advice string alpha n that Turing machine takes and does its computation. This can be written as a circuit. And let us call that circuit Cn. So this is again called, this advice is hardwired. In the simulation. And then it can decide for all these inputs of the fixed length n. So you can see that the size of Cn is some polynomial blow up. I mean, this Turing machine has n to the c steps, right? The size of n to the c is some polynomial blow up. I mean, simulation I think you can do even in quadratic. So, it is something like n to the 2c and which is polynomial in n, right. So, this means that we have shown that L is also in P/poly. It has poly-sized circuits, which means that we have shown both of them P/left hand side, right hand side equal. So, we have non-uniform circuits and we have non-uniform Turing machines. These are the same, these are equivalent concepts. So, non-uniform efficient circuits, and this side is non-uniform efficient Turing machines. Turing machines that take advice, run for polynomial time, or circuits that are of size polynomial, they solve the same problems and they can also solve uncomputable problems, right. That is what we have shown. Now, can these advised Turing machines, can they solve something hard as SAT? That is the next question you can ask. So, could Turing machine with advice solve SAT? Right, if these Turing machines with advice, if they are so powerful as to solve uncomputable problems, can they solve SAT efficiently? So, this is an interesting question, it is still open. But what we will show is an interesting polynomial hierarchy collapse. So, we will show the following theorem. This was done by Karp-Lipton. (1982). It's a classic theorem that says if you can solve SAT by polynomial size circuits, which means also Turing machines with advice in polynomial time and polynomial advice, then pH collapses to the second level. Okay. So, everything in the polynomial hierarchy is equal to sigma 2. So, it still does not say that NP will be P, but it says that NP to the NP is equal to everything above. So, sigma 1, sigma 2 may still be different, but this is a strong theoretical evidence again that SAT cannot be solved with poly-size circuits. So, one immediate consequence of this is thus Boolean circuits is a useful way to study NP hard problems. because suppose you show that NP is not in P/poly. So this Karp-Lipton theorem is saying that most likely SAT is not in P/poly. So NP is not a subset of P/poly, and this in particular would mean that P is not equal to NP. Right. So we can follow the route this is a feasible route because of Karp-Lipton theorem. Show that SAT is not in P/poly and then separate P from NP. Right. So NP SAT not in P/poly is a stronger conjecture than SAT not in P. Okay, so let's prove Karp-Lipton. So assuming that SAT is in P/poly, I mean the idea is that use circuits, SAT circuits. So if Cn solves SAT, then use them to find a satisfying assignment. Okay, so if Cn is solving the search for version, then you can also solve the if Cn is solving the decision version, then you can also solve the search for version, which is to actually find a satisfying assignment. And once you have the satisfying assignment, you can actually convert pi2 SAT to sigma 2 SAT. So use this to convert pi2 SAT to sigma 2 SAT, hence showing pi2 and sigma 2 equal. Okay, so this first thing is called self-reducibility. So we can use self-reducibility of SAT to basically you can set x1 to 0 or 1 and ask SAT itself which one is true. So once you know that, then you know that x1 how to fix x1, and then you can proceed to fix x2 and so on. Okay, so as soon as a circuit solves SAT or an algorithm solves SAT, you can also find an assignment, and once you find an assignment, that will help you in converting for all there exists to there exists for all. So which will imply that pH is sigma 2 pi 2 as before, right? That's the idea. So let's do see the implementation. So consider pi2 SAT instance. For all u, there exists V phi uv. Okay. Now, if SAT has, let's say, size m to the e circuit family, Cm, such that Cm phi given phi and u basically whether this satisfying assignment V exists. Okay, so U is given and then phi is given, and whether V exists or not. Okay, that is a SAT instance. So, suppose it can be solved, CM is solving that. Okay, so suppose this SAT instance is being solved. So, if we fix U, then V is the only unknown thing, whether it exists or not. So, it's a SAT instance, and so the circuit CM can solve it. That is what we are assuming, and say the SAT instance has size M. Okay, so we'll use the circuit corresponding to that size, which is CM. Circuit itself has size m to the e is some constant, and it is solving this. Okay, so using this CM, we will now try to find V. That we will do next.